Let us solve some questions from the chapter convection, and I'll be taking questions from both free convection and forced convection. And while solving questions, I'll be telling you about the important concepts and the important formulas that are being used or on which the questions are being asked indeed. Okay. So the first question is from free convection. A 320 centimeter high vertical pipe at 150 degrees Celsius wall temperature is in room with still air at 10 degrees Celsius. Okay. So the ambient temperature is 10 degrees Celsius. T infinity. Okay. This pipe supplies heat at a rate of 8 kilowatt into room by natural convection. Okay, that is free convection. Assume laminar flow. The height of the pipe needed to supply 1 kilowatt only is. Okay. So first tell me, what is heat transfer rate through convection? HA delta T. This is the heat transfer rate through convection. Okay. And when this vertical pipe is actually convecting heat into this room, it will be doing by its curved surface area. And the curved surface area of cylinder is pi dl. Okay. So is there any change in delta T? No, there is no change in delta T because in the second case also the wall temperature is 150 degrees Celsius of the pipe, this wall temperature. Okay. So when this is convecting heat, it will be convecting heat from its curved surface area. Okay. So delta T in second case is also same, and in the first case is also same. There is there any change in the heat transfer coefficient in the second case? No, because the second pipe is again placed in the same room. Okay. So can I say that Q1 is equal to H A is pi d L1. Okay. There's nothing given about the diameter. So we will assume that the second pipe also has the same diameter. Okay. So pi d L1 delta T. Okay. And for the second case, where we have to find the length of the pipe, and it's needed to supply 1 kilowatt only is, okay, PDL2, let the length of that pipe be L2. Okay. For the second case, this is for the first case where the length of the pipe is L1, which is 320 centimeters. Okay. And for the second case, let the length of the pipe be L2. Diameter is same. However, this figure is not drawn same. Let me just draw it. Yeah. L2. Okay. So if I divide both of these equations, this gets cancelled out, this gets cancelled out, this gets cancelled out, this gets cancelled out. So Q1 by Q2 is equal to L1 by L2. Okay. That is, heat transfer rate is directly proportional to its length. Okay. Longer the tube, higher the heat transfer rate. So Q1 is what? Q1 is 8 kilowatt, and Q2 you need to supply 1 kilowatt is equal to L1 by L2. L1 is 320 centimeter, and L2 is, if you are putting this in centimeter, you will get L2 in centimeters. Be careful that you have to put answer in centimeters. Okay, so we can proceed. So L2 is what? 40 centimeters. 40 centimeters. This is the answer. Okay. So it was based on the basic formula of the convective heat transfer. HA delta T. Let's move on to the next question. So this is 40. Consider a hot boiled egg in a spacecraft that is filled with air at atmospheric pressure and temperature at all times. Okay. Disregarding any radiation effect, given that disregarding any radiation effect, will the egg cool faster or slower when the spacecraft is in space instead of on the ground? Okay. So tell me, first of all, tell me, what is the basic driving force for natural convection? Buoyancy force. buoyancy force is the driving force for natural convection. Okay, and there is a number that signifies the magnitude of buoyancy force. What number is that? That is Grashof number in natural convection. Okay, so Grashof number. The mathematical formula for Grashof number is G beta delta T LC cube by nu square. This you must have studied. But what is the significance of Grashof number? What does it signify? Grashof number is inertia force into gravity force upon viscous forces whole square. Okay. Now, is there any gravity on space? There is no gravity on space. That means there will be no natural convection occurring. And if there will be no natural convection occurring, will the egg cool slower or faster? It will cool slower. Simple as that. So if there are no gravity forces, there will be no driving force for free convection. Okay, because we have to disregard any radiation effect. So the sole heat transfer will be dependent on natural convection. Okay. So let's move on to the next question. A flat plate of size 4 meter cross 4 meter at constant temperature of 80 degrees Celsius is subjected to parallel flow of air at 1 atm 20 degrees Celsius and 10 meter per second. Okay. So let's draw a rough schematic diagram. This is the plate. Okay. This is the plate. 4 cross 4. 4 cross 4. At a constant temperature of 80 degrees Celsius, this is 4. Four cross 4. 4 meters. 4 meters. And the air is flowing over it at a velocity of 10 meter per second, and its temperature is given as T infinity is equal to 20 degrees Celsius. Okay. The total drag force acting on the upper surface of the plate is measured to be 2.4 Newton. Okay. So when the air will flow over this flat surface, why? What is the reason for this drag force? Friction. Okay. This friction, due to this friction, there will be a drag force that will be acting on this upper surface of the plate. Okay. And it is measured to be 2.4 Newton. So F drag Fd is equal to 2.4 Newton. Okay. If air properties are the properties are given, the density is given, specific heat of air is given, which is in kilojoule per kilogram Kelvin. Change it in joules per kilogram Kelvin while putting it in the formula. Heat transfer coefficient is, okay, you have to find the heat transfer coefficient. Yeah. So we have some expressions related to the drag coefficient and the total drag force that you must have studied when you have studied this subject heat transfer. Okay. So there is one formula which is drag coefficient is equal to drag force upon half rho AV square. I cannot derive it in this question. I'm not going to derive it, but you must have derived it. Okay. So I'm directly writing the formula that this is the drag coefficient. Drag coefficient. Okay. This is the average drag coefficient. We had average also. Average drag coefficient. This is the drag force. Okay. This is density. This is the area on which this air is coming into contact, and this is the free stream velocity. free stream velocity, that is in this case is 10 meter per second. Okay. So if I have all the data, yeah, FD is what? FD is 2.4 Newton, and half rho is 1.204. Area, what will be the area? Area will be 4 cross 4, 4 cross 4, this area. Okay. So this is 16 meter square, and V is 10 meter square. Sorry, 10 meter per second, so 10 square, rho V square. Okay. So when you solve this, you will get CD, that is drag coefficient, average drag coefficient, and the value of average drag coefficient will be 2.4916 into 10 to the power minus 3. Okay. Now, why I have found out this average drag coefficient? Why? Because I actually have to find heat transfer coefficient. And do you remember something about Reynolds analogy? In that analogy, I have this term heat transfer coefficient. Let's see. So Reynolds analogy is Stanton number, local Stanton number, to Prandtl number raised to the power 2 by 3 is equal to local drag coefficient by 2. Okay. So if I replace here the average drag coefficient, here will be Stanton number, Prandtl number raised to the power 2 by 3, CD by 2. Okay. That is why I have found out the average drag coefficient, because Stanton number is equal to H by rho CPV, and Prandtl number raised to the power 2 by 3, which is equal to CD by 2. Prandtl number is given to us or not? It's not. Yes, it is given to us. Right. Yeah. If it was not given to us, the properties of air would have been given to us. Prandtl number is mu Cp by K. So either mu would have been given to you, or Cp is given to you. Yeah. Cp is given to you, and K would have given to you. But instead of giving mu and K, they directly gave us Prandtl number. So Prandtl number is 0.709, 7309. Yeah. So this is 0.7309 raised to the power 2 by 3 is equal to CD by 2, and H we have to find out. Rho is 1.204, Cp is 1.007 kilojoule per kilogram Kelvin, so that means it will be 1007 joule per kilogram Kelvin, and V is 10. The only term that you have to find is H, because CD is what? CD is this 2.4916 into 10 to the minus 3. So CD is 2.4916 into 10 to the minus 3. Put this value in this formula, in this expression here. You will get H. H will be equal to, H is coming equal to, I guess, the value is 18.62. 18.62 watt per meter square degree Celsius. 18.62. This is the answer. So whenever the case of forced convection comes, and air or some fluid is flowing over a flat plate, do think of Reynolds analogy if you have to find heat transfer coefficient. Okay. However, sometimes it is mentioned in the question paper that you have to use Reynolds analogy, but if it is not mentioned, you can still use Reynolds analogy, because we would not have been able to solve this question without using Reynolds analogy. Okay. Because drag force is given to you, so drag force will directly lead you towards the average drag coefficient, and average drag coefficient is used in Reynolds analogy. So Reynolds analogy has that term that has the heat transfer coefficient as well, and the drag coefficient as well. So this was about Reynolds analogy. This was an important question. Okay, so take care to remember this analogy and use this in the exam. Next question. Next question is from heat transfer coefficient and Nusselt number. The chapter is okay. 40 liters of water is heated from 15 degrees Celsius to 45 degrees Celsius. 40 liter. 40 liter, that is 40 into 10 raised to the power minus 3 meter cube. SI units of water is heated from 15 degrees Celsius to 45 degrees Celsius. This is delta T of water by a 6 centimeter diameter spherical heater whose surface temperature is maintained at 85 degrees Celsius. So this becomes T infinity. Okay. The properties of water for this case are, okay, Grashof number is given. So that means it is a case of natural convection. Okay. Grashof number is given. 2.4 into 10 power 8. So thermal conductivity is given, rho, Cp and all this data is given. Prandtl number is also given to you. The Nusselt number is given by, okay, the expression for Nusselt number is given to you. How long the heater should be kept on. Okay. So first of all, we can find out the heat required to change the temperature to actually heat water from 15 degrees Celsius to 45 degrees Celsius. Okay. So Q required will be mCp delta T. Okay. This is the heat required to actually raise the temperature of 40 liters of water from 15 degrees Celsius to 45 degrees Celsius. Okay. So M is in kilogram here, but here it is in, this is volume, but density is given. So rho into volume will give me mass. Okay. So this is 996 into 40 into 10 to the power minus 3. Now this mass is in kgs. Cp is 4.178 into 10 to the power 3 joule per kilogram degree Celsius, and delta T is 45 minus 15, that is 30 degrees Celsius into 30. So Q required will be, the value will come out to be, this is 4.993 into 10 to the power 6 joule. Okay. This is the Q required, that is heat required. This will be in joules. Okay. Now I have to find out that what is the heat given by the heater to this water per second. That is, I have to find heat transfer rate. Okay. And how can I find out that? The mode of heat transfer rate in this case is natural convection. So Q dot, or in heat transfer we just write it as Q, but I am using Q here for this equation. So Q dot is equal to HA delta T. This will be in watts. Okay. Now what is what? Joule per second. So whatever this answer will be, this is heat transfer rate. That is, this much joule of heat is given to the water per second. Okay. So this is joule per second. So A, can I find out A? Yes. This is a spherical heater. So this is the surface area of sphere, which is 4 pi r square. 4 pi r square. Okay. Be careful that you have been given with diameter, not radius. Okay. Radius is 3 centimeter. 3 centimeter. Okay. Right. And what will be delta T in this case? The surface temperature of heater is 85 degrees Celsius. Okay. But the temperature of water is continuously changing because it is rising from 15 degrees Celsius to 45 degrees Celsius. So what we do in this case, we take the average of both the temperatures. That is 45 degrees Celsius plus 15 degrees Celsius divided by 2. That is 60 by 2, 30. 30 degrees Celsius. Okay. Take the average of these temperatures. Because the temperature is continuously changing, it is rising. Okay. So this is Ts minus T infinity in this case. So area you know, delta T you know, you have to find Q dot, but for that you need H. And we have the relationship of Nusselt number with us, and Nusselt number is equal to HLC by K. Okay. So Nusselt number is equal to HLC by K. What is this LC? LC is the characteristic dimension, and for a sphere, characteristic length is its diameter. Okay. So can you find Nusselt number, the value of Nusselt number for from this expression? What is this expression? Nusselt number. So yeah. So the expression is 2 plus some data. This is what R is what? R is Rayleigh number. Okay. And Prandtl number is given to you. What is Rayleigh number? Rayleigh number is Krash number into Prandtl number. Okay. So are we given with Grashof number? Yes, we are given with Grashof number and we are given with Prandtl number, so we can find out Rayleigh number. Okay. So I'm not going back. I'm directly writing the value from here. So Rayleigh number is what? It is 2.4 into 10 to the power 8, and Prandtl number is 3.12. So when you solve it, Rayleigh number will be equal to 7.49. 7.49 into 10 to the power 8. See, I'm trying to cover all the formulas, all the important expressions that you must have derived while studying heat transfer. Okay. I'm trying to cover all those in the equations, in the questions. Sorry. So Rayleigh number is Grashof number into Prandtl number. So this is 7.49 into 10 to the power 8. Okay. And what else is required? Prandtl number is required for that expression. Prandtl number is 3.1. Put this data in this formula directly. Okay, and solve it. Be careful while solving it. Do not commit any calculation mistake. Okay. So you will get Nusselt number as 87.43. 87.43. Okay. Now as I have Nusselt number which is equal to 87.43, I can find out H, because Nusselt number is equal to HLC by K. LC is the diameter in this case is 0.06 meter, 6 centimeter, right? Yes. And K is 0.6515. 0.6515. Nusselt number is 87.43. So you can find H from here. So H is equal to, H comes out to be 949.344 watt per meter square Kelvin. Watt per meter square Kelvin. Yes, this is RH. Now I have heat transfer coefficient, the value of heat transfer coefficient with me. What I can do, I can put this value here. Okay. And this will give me my answer. Okay. Area is 4 pi r square, delta T is 85 minus 30 degrees Celsius. Explained that why I have taken 30, because the temperature is changing. So you take average of that. These cases. So Q will be, I'm writing the answer directly. Q, that is a rate of heat transfer by convection, Q dot, sorry, is equal to the answer. What's the answer? It is I've not solved it. It is, I guess, 590.5 watt. Okay. 590.5 watt. We'll get this the rate of heat transfer by convection. Okay. So you'll get 590.5 watt. Whatever be the answer. Okay. This is, I guess, this is the answer. 590.5 watt. By that is the heat transfer rate by convection. Yeah. Okay. Now I have to find the time for which the heater should be kept. Okay. So I have explained that this is the heat required in joules. Okay. This I have found out in watt. That is, this much joule of heat it is giving to the water per second. So if I multiply this term with time, I'll get my answer. That means, let me rub something. I'm rubbing this. Okay. This one also. Yeah. So Q dot convection into T is equal to Q required. Simple. This is in watt, that is joule per second, into second will give me what? See, we can just play with the units. See, that is why I always tell you that take care of the units. Okay? If you are clear with your basics, you can solve any question. So Q convection is 590.5 watt. I do not trust this value, so I will be just writing this H949 HA delta T. I have not solved this, so this HA delta T is equal to Q required, which is Q required. What was the value? 4.993 into 10 to the power 6. 4.993 into 10 to the power 6 joule. Okay, H is 949.344 watt per meter square into area is 4 pi r square. R is 0.03 square into delta T, which is 85 minus 30. Yeah, that's 55 is equal to Q required into T. Sorry, into T into time, small t into T is equal to Q required. Okay. So find time from here, which will be equal to some seconds, 8455 seconds. Convert it in hours, that will be 2.348 hours. And the subsequent option will be, where are the options? 2.32, 2.32, 2.35. Oh, these are very close. So 2.35, this is the answer. This was again a nice question. Okay. Let's move on to the next question. This is from boundary layer thickness. So water at 20 degrees Celsius flows with a velocity of 10 meter per second over a flat plate which is maintained at 80 degrees Celsius. Okay. So the velocity of the free stream is given, that is 10 meter per second. Find the thermal boundary layer thickness at 1.5 meters from the leading edge. Okay. Viscosity and thermal conductivity of water are. Which viscosity? Pascal second. See the unit. So that means it is dynamic viscosity. That is mu. Okay. So Pascal second and thermal conductivity is 0.65 watt per meter. So I have to find the thermal boundary layer thickness. Okay. So for that, I have to find the hydrodynamic boundary layer. Okay. And before that, let us find out the Reynolds number. So Reynolds number is rho v LC by mu. LC is again characteristic length, and for a flat plate, characteristic length is equal to L. So where do you have to find the thermal boundary layer? You have to find the thermal boundary layer thickness at 1.5 meter from the leading edge. So LC is equal to L is equal to 1.5 meter in this case. So rho, water is flowing, so rho is 1000. Take rho as 1000. However, in the question it will be given. It will also be given. Density of water will also be given. So 1000 into V is 10 meter per second, 10, and LC is 1.5 here, and mu. What is this mu? Mu is 4.5 into 10 to the power minus 4 Pascal second. So when you solve it, Reynolds number will be equal to the value of Reynolds number. This is coming equal to 3.33 into 3.33 into 10 raised to the power 7. Yes, it is 10 raised to the power 7. Pass. No units. Sorry. So it is coming. Reynolds number is equal to 3.33 into 10 to the power 7. Dimensionless. Yeah. So what this states that the flow is turbulent. Why? Because the critical Reynolds number where the transition occurs, REC, is where the transition from laminar flow to turbulent flow occurs is 5 into 10 to the power 5. Below this number, the flow is laminar, and above this, or in some books, it is 7 into 10 to the power 5. It is considered as turbulent. So this flow is, this Reynolds number is larger than both the numbers. Okay. In some books, it is written that the critical Reynolds number is 5 into 10 to the power 5. Below that, the flow is laminar, and above that, the flow is turbulent. but in some books it is written that the if the Reynolds number is less than 5 into 10 to the power 5, then it is laminar, and if it is greater than 7 into 10 to the power 5, then the flow is turbulent. But in our case, this Reynolds number is greater than both the numbers, so this flow is turbulent. Okay. Now this flow is turbulent. Okay. Let's find out the next number, that is Prandtl number. Prandtl number is mu Cp by K. Okay, mu Cp by K. What is mu? Mu is 4.5 into 10 to the power minus 4, which is 4.5 into 10 to the power minus 4. And Cp is given to you, Cp is not given to you. You can take it as 4.18 into 10 to the power 3 joule per kilogram Kelvin upon K. K is what? K is 0.65 watt per meter. 0.65 watt per meter. Okay, so Prandtl number is equal to what? It is equal to 2.8913. It is equal to 2.8913 or 9? Yeah, 13. 2.8913. Now, I'm going to find out hydrodynamic boundary layer. Okay, hydrodynamic boundary layer has an expression 0.37x upon Reynolds number raised to the power 1 by 5 for turbulent boundary layer case. Okay, because the Reynolds number is greater than 3.33 into 10 to the power 7, that is a case of turbulent flow. So in this case, the hydrodynamic boundary layer is given by 0.37x upon Re raised to the power 1 by 5. Okay, so 0.37x, x is what? 1.5, because you have to find the boundary layer thickness at 1.5 meters. Reynolds number is 3.33 into 10 to the power 7 raised to the power 1 by 5. So you'll get the hydrodynamic boundary layer thickness, which will be equal to 17.4 mm. 17.4 mm. And now, what you will do that delta upon delta thermal is equal to Prandtl number raised to the power 1 by 3, and you will get your answer as by this formula. Okay, because you have delta with you, you have Prandtl number with you, you can find out delta thermal. But this is wrong. All of you will do this, and this is wrong. Okay, because this is a case of turbulent flow, and in turbulent flow, delta is approximately equal to delta thermal, and which will be equal to 17.4 mm. Okay, this was the point. That is why I found out Prandtl number. There was no need to find out Prandtl number, but I wanted you to commit mistake and think like this. But always remember, for the case of turbulent flow, the hydrodynamic boundary layer is approximately equal to the thermodynamic boundary layer. Okay, very important, very very important. Do not commit this mistake. But this is wrong. Okay, so the answer will be what? Answer will be 17.4 mm only. This will get in meters. Okay, because I have put the length in meters, but I have directly written here in. This is yes. Okay. Next question. This is a very lengthy question. It seems that it is a very lengthy question. Many of you students, what they will do, that they will leave this question without even reading it. But at least read the question before leaving it. Sometimes some extra data is given, or which is not used, and you can lose marks, and your gate rank will shift by some 500 or thousands. So at least read the question and then decide whether you have to leave it or not. Let's read this question. This is air is flowing at a velocity of 3 meter per second. 3 meter per second, perpendicular to a long pipe as shown in the figure. Okay. So this is now a horizontal case of a horizontal cylinder. Okay. And for horizontal cylinder, characteristic length is its diameter. The outer diameter of the pipe is 6 centimeter. which will be the characteristic length in this case, and the temperature at the outside surface of the pipe is maintained at 100 degrees Celsius. Great. The temperature of the air from the far from the tube is 30 degrees Celsius. That is, this is the ambient temperature, T infinity, and this is the surface temperature, 100 degrees Celsius. Data for air is given, that is kinematic viscosity is given. Kinematic viscosity is given, that is mu by rho. So whenever the question is of this convection, you will have to use, or in many cases you will have to use a Reynolds number. So Reynolds number is rho VLC by mu or VLC by. Okay. Thermal conductivity is given to you using the Nusselt number correlation. Nusselt number correlation is also given to you. Everything is given to you. You have to find the rate of heat loss per unit length from the pipe to the air. See, this is a very simple question. It seemed a tough question, but it is a very simple question. You just have to find the rate of heat loss per unit length from the pipe to the air up to 1 decimal. What is the rate of heat loss? What is the formula? It is Q dot, or in heat transfer we just denote it as Q. Whatever is your wish. Q is equal to H A delta T. Okay. How can I find H? Nusselt number correlation is given to me. This is the relation. Okay. And Reynolds number I can find out because I have V. V is 10 meter per second. No, sorry, 3 meter per second here. And LC is diameter in this case, which is 0.06 meter. And nu, kinematic viscosity, is given to me. So I can find out Reynolds number. I can find out Reynolds number. I can find out Nusselt number. If I find out Nusselt number, I can find out H because I have D and K. Simple. Okay. So let us do this. So Reynolds number. The value of Reynolds number will be V is 3 meter per second. LC is what? LC is what? What is this LC? LC is what is the diameter? 6 centimeter. That is 0.06 meter. V D by nu. Nu is 18 into 10 to the minus 6. 18 into 10 to the minus 6. So this comes out to be what is the value? This is 10,000. 10,000. Okay, it's flowing over a pipe. So Nusselt number, when you put this value in this expression, 10,000 raised to the power 0.8 into 0.024, you will get the value of Nusselt number, which I am directly writing, which is equal to no value is written of Nusselt number. Okay, so directly solve this. H 0.06 by K. What is this K? This K is 0.03. 0.03 is equal to equated 0.024 into 10,000. Now solve it. So directly get the value of H. Okay. Now you can solve it. And H is equal to what? H is 19.0187. 0187 watt. In what units? Watt per meter square. Okay. This will be H with me. Now I have H with me. Area I can find out. Area is what? Pi d L. And L is not given, but they have asked us to find the rate of heat loss per unit length only. So I can take that L in the denominator of Q. Okay. Show you. So this is what? So now Q, let me change the color. So Q is equal to HA delta T. Okay. And H is 19.0187. A is pi dl delta T. What will be delta T? Delta T will be 100 minus 30. Because the outside surface temperature is 100 degrees Celsius and the air is coming at 30 degrees Celsius. So the heat will be convected from the surface of this pipe to the air. Okay. So this is what? This is 100 minus 30 delta T. Take this L below this Q. Okay. This will be H pi D 100 minus that is 70. So Q by L is what? Watt per meter. Solve this and get the answer. Very easy question, And many of the students, they'll look at the question and they will leave the question without even reading it. So the answer to this question is 250.94. So Q by L is 250.94 watt per meter. Just rub it. 94 watt per meter. Okay. Let's move on to the next question. The last one for this video. Okay. We will solve some more questions of convection in the coming videos. But for this video, this will be the last one. A hot plate of area 0.2 meter square is maintained at a temperature of 59 degrees Celsius by a 100-watt heater. Okay. So there is a hot plate, okay, which is maintained at a temperature of 59 degrees Celsius. 59 degrees Celsius by a 100-watt heater when the room temperature is 20 degrees Celsius. Okay. So the room temperature T infinity is 20 degrees Celsius. Okay. And this plate is maintained by a heater. A heater is there, which is giving 100 watt of heat to this plate. Okay. The appropriate convection coefficient, okay, the relation is given. It is 2.512 delta T raised to 1/4 watt per meter square Kelvin. Taking heat transfer from plate is by convection and radiation. The percentage of heat lost by radiation is. Okay. Again, a simple question based on the fundamentals of energy conservation and the basic expression of convection. So this heater is giving 100 watt to this plate. Okay. And this plate is in a room. What will it do? They have said that taking heat transfer from plate to room, they meant to room, is by convection and radiation. So this 100 watt of heat will be convected to room and will be radiated to room. So let this be Q convection and let this be Q radiation. Okay. So can I say that 100 watt is equal to Q convection plus Q radiation? Simple energy balance. Okay. This 100 watt is going from heater to this plate, and this heater is convecting heat to the room and this heater is convecting heat to the room and radiating heat to the room. Okay. And that will be equal to the heat that is coming into the plate, which is 100 watt. So 100 watt is equal to Q convection plus Q radiation. Okay. That is the heat transfer rate. Okay. So I have been given with appropriate convection coefficient. Q convection is what? Q convection is HA delta T. Okay. I can find out H. How? Because H is equal to 2.512 into plus Q radiation into delta T raised to 1/4. What is delta T? What will be delta T? The plate temperature is 59 degrees Celsius. The room temperature is 20 degrees Celsius. Okay. So the heat is convected from the plate to room. That means delta T will be 59 minus 20. 59 minus 20 raised to the power what? 1/4. So solve it. H will come out to be what? 6.2774 watt per meter square Kelvin. Okay. This is H. So when you get H, can you find out the heat transfer rate by convection? Yes, because area is given to me and delta T. So Q convection is equal to H. H is what? 6.2774. Area is given to you in the question, which is 0.2 meter square only. Into delta T is 59 minus 20. Right? 59 minus 20. Yeah, that is 39. Find this. This will be in watt. heat transfer rate by convection. Okay, this answer is 48.6963 watt. That means 100 minus 48.963 watt of heat transfer is occurring by radiation. So this becomes equal to Q radiation is equal to, when solve it will be 51.036 watt. Okay, and you have to find the percentage of heat loss by radiation, that is 51.036 upon 100 into 100, that gets cancelled out. So 51 point Q radiation percentage is equal to 51.036%. Okay, this is your answer. Based on simple concept, simple energy balance, and simple concept of convection. And this is how the questions in the gate are being asked. They hit on your basics. So this was all for this video. We'll solve some more questions related to convection in the next video.